Hello, I'm Joep from Statistics Netherlands, and in this video I'm going to present a paper with Quinten and Meertens on the algorithm versus the chimps, on the minima of classifier performance metrics. There's a wide array of performance metrics that are used to assess the quality of predictions of models, machine learning models, in classification problems. But most of these metrics are sensitive to class imbalance in the data, and this makes the interpretation of the metrics more difficult and also hampers the comparison between applications. Possible solutions are to balance the sample or to balance the metrics, but here I'm going to present an alternative, and that is to compare these performance metrics with how the proverbial chimps at the zoo would perform if they would randomly guess the different classes. And in this talk, I'm going to focus on binary classification problems. So in cases where you only have two classes. All of the performance metrics are based on the confusion matrix. So in this case, we have n instances in our test set, and one of which are in the positive class. And then we have the model that predicts x true positives and has y false positives. And with that information, we can fill the rest of the confusion matrix. And then we can calculate the performance metrics. The most common ones are the true positive rate and true negative rate, and the positive predictive value and the negative predictive value. True positive rate is also called sensitivity or recall, and the true negative rate is specificity. Positive predictive value is also called precision. In this talk, I'm going to use alpha to indicate the proportion of positive cases in the test set. And this proportion is also linearly transformed to a scale of ranging from -1 to 1, so that if the classes are balanced, so the data are balanced, then this imbalance coefficient equals 0. If we then look at the confusion matrix, if for the proverbial chimps at the zoo, then it would look like this. So we would randomly guess the positive class with the probability g. So a proportion 1 minus g of all these numbers will go into the negative class. And for g, we can specify a number of strategies. For instance, we pick g equal to a half. That would mean tossing a fair coin, or we could also use the proportion that we observed of the positive class. Then g would be alpha, and we could also, for instance, always predict the most common class, so the mode. This table may look a bit complicated, but I'll walk you through it. Here's a list of commonly used performance metrics with the definition, and I'm assuming you're familiar with these. And our contribution, the main result, is the expected value of these metrics if you would randomly guess the positive class with probability g. So here we have accuracy, these four metrics I introduced earlier, and the area on the curve and J, Jouden's J index, that look at the trade-off between these two. Markness looking at the trade-off between these two, and then the Matthews correlation coefficient, and the positive and negative F1 looking at the harmonic mean of either these two or these two. And now if we look at the expected value for Jouden's J, it's always 0. For Markness and MCC, it's also 0, except for a small term that can be ignored unless your test set is very small. Area under the curve has an expected value of a half. And then these are also constants. So for true positive rate, true negative rates, either g or 1 minus g. for these alpha 1 minus alpha, so relatively straightforward. But for the accuracy and the F1 are more complicated. Unless G is half, then the expected accuracy is also half. But if you choose G equal to alpha, this becomes a quadratic function. And the F1 is a function of nonlinear function of both alpha G, but also the sample size. And I'm going to show you an example of this function later on. We can do the same thing for balanced performance metrics. I'm not going to go into this for time reasons. And once we have the expected value, then we can min-max normalize our metric so that it runs from 0 to 1, where 0 means the model is not performing better than the expected value, and 1 means you have perfect prediction. In the literature, we can also find the Heidt-Skill score, or Cohen's kappa, and that is the same as the min-max normalized accuracy, where G would be equal to the proportion of the instances that the model labels as positive. But this is not really a chimp strategy or a random guessing, because for this you need to have a model, and you can only calculate that after you have constructed the confusion matrix. So here's an example using 1,000 instances that are equally allocated, but depending on delta, this allocation may shift. And we are assuming that the model has a true positive rate of 0.6, which means that 60% of the positive cases will be true positives, and the true negative rate of 0.8, which means that 80% of the negative cases will be true negatives. With that information, we can fill the rest of the table. And here I'm showing the F1 score of this model as a function of the imbalance coefficient delta. And you can interpret these as comparing different applications or data sets where the class imbalance is different. What we see is that the F1, the positive F1 increases with delta, and the negative F1 always decreases with delta. You can get rid of this sensitivity to class imbalance by balancing the metric, which means that you just set delta to 0. The alternative that we propose is that you compare this score to the score that you would get if you randomly guessed a positive class with this probability G. In this case, we choose G equals to half, which means tossing a fair coin. And then what you get is this normalized positive F1, and it actually has an optimum here at a certain delta, which means that if delta is larger, the positive F1 is higher, but the normalized positive F1 actually decreases. We also see is that there is a zone here between these white points where the positive F1 is larger than the negative F1, but the normalized positive F1 is actually lower than the normalized negative F1. So in conclusion, we propose to min-max to normalize the classifier performance metrics, using as minimum the expected value when randomly guessing the positive class with a certain probability G. We give the approximation for the expected value for a number of commonly used metrics, where we assume that the number of true positives and false positives follow a binomial distribution, and this gives an intuitive interpretation and makes metrics and applications comparable. There's no need to balance the sample or the metric, and in future research it would be interesting to generalize this idea to multi-class classification regression and apply them to empirical studies. Thank you for watching.